Good morning, everyone. I'm delighted to be here, and I do learn myself a lot from my peers, so I hope that we can find some interesting links today. I will today describe a bit of the background of my own company, IBM Research, a very short bio of my own path in life, and then I will provide you some insights into how industrial research environment looks like, and the two other forces that takes us from the two directions. So one is the academic interaction, and the other one is the client interaction. And I'll try to make it interactive as I can, but due to the short time, I hope that we can do something. So anyone can guess how old is IBM? Give me some numbers. Come on, people, numbers. 100. Okay, actually that was very close. 103. It was incorporated in 1911, which is remarkable. But the company actually exists from 1888, which is really quite ancient. Okay, you will have to extrapolate what happens outside the screen. I don't know why it is like that. So the IBM has a global footprint of 12 labs across the world with about 3,000 scientists dedicated to try to push the edge of the envelope. We do things that are both cool and also uncool that makes an impact upon the world. The annual investment is about $6 billion in research. That's our brag sheet. So, we have about 6 Nobel Prize laureates, equivalent of 6 Turing Award winners, which is the equivalent of Nobel Prize in computer science. And recently we actually got even the Emmy Award, which is, I can actually change it to this display if you want. I don't know whether that would help. Would that be easier if I will just do something like that? Yeah? Okay, guys. Sorry for that. It's a different form factor. But then I will have to skip some of the slides. So we actually got an Emmy Award, surprisingly, for the linear magnetic recording tape, something that we all believe that is part of the ancient past, but apparently it is still in use in that industry. And some brief history. I won't go through each and every one of those entries, but in 1944, the Mark I computer, it was the size of probably 17 meters by 3 meters, 5 tons of weight. It took 6 seconds to do multiplications, 12 seconds to do division. So you can imagine that, and that was the state of the art back then. 4 years later, the selective sequence electric computer was actually 250 times faster already. Fast forward 1957, the Fortran was actually invented in my lab. So I agree, you do need to learn how to program, and then actually that's very, very useful, not only Fortran, of course. 1966, the DRAM, which probably is something that you have in each cell phone, computer, or any other electronic device you may use. Geoff mentioned fractals. A colleague of mine in my department, Mandelbrot, was the one to come up with the ideas of fractals back in '67. The guy actually, it's interesting you mentioned that, he died at a very fractalish date. It was October 10th, 2010. 10-10-10. So, so some other things there. The reduced instruction set computer, which is the basis of most workstations, the XChem laser, which people are using now for LASIK surgery, 2 Nobel Prize in scanning tunnel microscope, high temperature superconductivity. Anyone knows about the Deep Blue? Anybody heard about it? Who have heard about the Deep Blue? Okay, so back in '97, that was the computer that beat Garry Kasparov in chess. Look, moving into the forward, actually 3 years ago, we had the Watson system that played Jeopardy against the 2 best contestants, and actually it beat both of them. So now IBM is looking into a new direction, which is called cognitive computing, trying to bridge between our abilities and the computer's ability to provide insights. Lastly, and again, I apologize that you cannot see it, so maybe I will try to make it even slightly smaller. Does it get better? Okay. I hope that your vision is good. We'll talk about it in a second. Last year we announced the development of a new neuromorphic processor. It's called the Synapse. This chip is actually constructed physically like a synapse rather than the conventional von Neumann architecture. I don't know how much it tells you guys, but it's a very, very different way of thinking about compute and how compute should be delivered. So if you have any questions, we can talk about it later. So I'll skip some of those that were actually hidden. And now I'll talk about myself. There's actually a small entry here that I saw Geoff mentioning about the military background. I won't say much about mine, but after I got released from the Air Force, 8 years in service, I did my PhD in medical physics in UCL. Then broadening my horizons a little bit, I did my postdoc at Emory University in the mathematical sciences department. And currently my position is a research staff member in the math sciences and analytics department in IBM. So that's a brief history of my own. My own research, in case you have any questions later on you would like to associate, is in ill-posed problems. I will have to go this mode because it's a bit animated. We would like to be able to infer some of the parameters either inside one's head or in the subsurface or wherever. In most countries this is illegal. So we come up with some experimental design to try to figure out how to collect data externally in order to figure out what's going on inside. Then we often have a predictive model which associates the measurements and the data, right? So this F links between the model, the parameters that we collect, and the data that we collect. And then these problems are actually ill-posed. So if we try to do a naive inversion, we typically do something like that. We try to find a model that the predictions of which for the data would be as close to the true data that we collected, right? And if you would try to do that, you typically not go too far. So here is an example you see here. That's the E. coli bacteria in a microscope. Now imagine you ask an undergrad student, because I know that there are grad students here, you ask him to take an image of which, and the guy was actually wasted last night. He went to the bar, and the camera was not in focus. There was dust on the lens. This is what he collected, the image in the middle. And if you would like to get back to the original image, just by trying to minimizing the mismatch of the data, he would end up with this image, and probably that grade for the semester, right? So, so what we typically do is we pose these problems as optimization problems that have two components. One is a data misfit term. The other part is a regularization term that incorporates a priori information we have about the solution. And taking a more holistic perspective upon this question, and again I apologize for the fact that some of it is cut, but there are multiple questions we can ask ourselves in order to resolve that problem in a better way. So as optimizer, we may ask ourselves, okay, how can we optimize this faster, bigger, and so forth? How can we improve the observation model? So if you're in the physical sciences, you may be more familiar with that. How can we extract more information already from the measurement? So Thomas was mentioning earlier the design explorer. That's really a similar objective. What should be the right metric for quantifying the discrepancy between the data and what you predict the data to be? How can you incorporate a priori information in a better, more intelligent way? Can you supplement the information from multiple sources to provide one unified understanding of what you're trying to reveal? Often we are not really interested to get a single estimate. We are interested to explore the complete posterior distribution of the solution. How can you sample that in a sensible way? And lastly, many times we are not really interested to get that single estimate. We would like to ask a bigger question, such as a design question or a decision based upon what we would like to reveal. So for instance, I managed to get an MR image of a patient. I'm not really interested to see that image by itself, even if it is beautiful. I'm interested to know whether that patient has a tumor or not, right? There is decision that I'm really interested, and sometimes I don't really need to go through the entire tedious process in order to get there. So that concludes my part of the introduction on that thing, and now I'll explain a little bit about industrial research environment. So, Geoff mentioned the emotional intelligence. Many of today's challenges are no longer tackled by a single researcher. So back in the 70s, people found it very, very popular to do IQ tests. I don't know whether any of you have done those. Recently, people are talking about collective intelligence, right? If you look at the wiki definition, it's intelligence that is shared among group, emerges from collaboration, collective effort, a competition of many individuals rather than a single individual. Now, some of the nice examples for that is the success of Wikipedia, Linux, CAPTCHA. So most of you know that when you do a CAPTCHA, one word is actually used for authentication. That's the automated Turing test. The other word is just actually helping to identify some words that were difficult to identify for the benefit of all of us. Foldit, anybody is familiar with the Foldit project? Only, okay. So really briefly, for 15 years in the University of Washington, they were trying to identify some structure associated with AIDS-bearing virus. They failed to do that for 15 years, and then at some point they say, okay, let's crowdsource the answer. Let's make a game that people will play, and the game will actually help us to get the answer. They did it, and successfully, after 3 weeks, they got the right answer, which is incredible. Most of the participants are actually completely ignorant in the field that was required. So that really tells you how much crowdsourcing can really help. MIT Sloan Center for Collective Intelligence actually extend that definition of collective intelligence towards collaboration also with machines. So we are not talking only about collaborations among people, but potentially man and machine collaboration, which is very interesting. And IBM is into cognitive computing, which is trying to leverage those ideas. So obviously, collaborative research environment involve a lot of teamwork, and that was mentioned earlier. There is diversity of skills, and one needs to know how to bridge among them. We do try to foster a collaborative ID creation environment. So we have some things that are remotely related to or resemble Shark Tank game. So people are coming up with their own propositions for neat ideas that are completely outside the research field, and other people crowd vote whether they would like to fund it or not, and we let those wild ducks get expressed. Just an example of a collaborative research environment. This is a project that I cannot tell you anything about. It's a project with DARPA, but it involves both physicists, material scientists, and what can we do? We also need those mathematicians in the picture. Beyond diversification of skills, since we are a big company, and there are other companies that also tackle a broader and versatile portfolio of problems, the scope of problem is much, much broader, and that forces one to work outside the comfort zone, and it fosters some continuous learning and professional evolution. You cannot just say, okay, I'm an expert in one field, and this is where I'll stay. You really have to step out. Here is an example for that. I will not tell the name of the company, but we were trying to help a company design the process of generating individualized contact lenses. So your eyes actually can provide better than 20/20 or 6/6 vision. You can have supervision if you correct not only for first order, but for higher order aberrations of your eye. Their process is somewhat similar to 3D printing, but it is far more complicated. So it involves some thermochemical, fluid dynamic things that are not highly or easily predictable. We help them to build a predictive model, and on top of that, an optimization process, so that we can essentially design those lenses to fit exactly what they would like to have. Now, obviously, when you work in industry, there is a real requirement to do things that to work on problems that of real life. And unfortunately, I would say, from my perspective, work with real data. A lot of people talk about big data. My own preference is to work with small data, or actually with no data. But reality is reality, and we have to deal with that. So you need to be able to deliver results that are useful. Beyond useful, they have to be robust, scalable, and effective. And it sounds trivial, but it's far from that. So I'll give you another example here. This one is animated as well. So in oil production, you know, you have those nodding donkeys, and you would like to, you collect some data through those. So you know more or less what is going on at the well sites. Every once in a while, you may afford doing some localized, doing some well logs. And then once in a while, you can bring in a seismic survey into the game and try to understand what's going on between those dots, right? But this is a problem that is actually ill-posed, right? There's a lot of things that you don't know, and if you would like to be able to characterize what's going on in the subsurface and control that, you really need to be able to connect all those heterogeneous sources of data into something which is unified and makes a lot of sense. So we worked on that project, and we proposed, so most simulators offer sensitivity capabilities only for the production wells. They don't really know how to associate those seismic sources of data. We propose them to use something which is called virtual wells. So those wells are following the trajectory of the seismic trace. And eventually, after all those efforts, we managed to get, so these are images of saturation. So you can see red is more oil, blue is water, from 3 different dates. So this is what they managed to do before we incorporated the seismic. After we incorporated the seismic, I'll do it smaller. This is what we managed to get, which is far more consistent with what the seismic itself tells us. But you ask yourself, okay, that doesn't look much different, right? This tree looks relatively similar to this tree, correct? Now imagine that each pixel here is $1 million, right? So making that slight mistake is really impactful. So I'll skip those, and then now let's talk a little bit about academic interaction. So teaching, it really depends on your perspective. It can be a pain, it can be fun, it can be both. Some of us do serve as adjunct professor in universities around. It's really up to one's own preference. Student interaction, I do say that we would wish to have far more. We do have internship programs like in Google, but obviously internship is something which is short term. I wish we would have more interaction with students. I think that this is something we definitely need to work on. But that's the reality for now. This is an example of a project that I did with a summer intern. She came for 10 weeks. Actually, she did 2 projects, so we managed to get 2 publications and a patent for her short stay. We were trying to prove wrong George Box's statement that all models are wrong, but some are useful. We actually wanted to say, you can take the best you can do with physical modeling, so physics-based modeling, PDEs and so forth, and combine it very nicely with data-driven modeling and get results that are superior. So if you have a model that is good, but you would like to get higher fidelity or any other property, you can do that. And we managed to prescribe a generic way to do that, and that worked very nicely eventually. We do collaborate with our academic peers. So joint publications, conference chairing, joint patents, internship programs, all of those are in place. We do provide funding and awards for both students and academics. That list of universities on the right is just those that I personally or directly work with. There are many others that the corporate as whole is dealing with. Obviously, you better establish intellectual properties agreement before you dive too deeply. I don't know how much of a concern it is for you guys now, but this is something that if you would be in an industrial environment, you would probably understand a little bit better. Here is an example for such a project. So we have, and Thomas was mentioning survey design. So survey design for well post problem is something that people have established for many years. It's a well-known research topic. When you come to ill post problems, when we started our research, actually there were only 2 studies that we found, and they were for small-scale problems. So collaboratively with the University of British Columbia, we came up with a new theory, practical algorithms. And the nicer thing of all of this is that everything was open, so it's open source. Everything we produced together is available on the web. You can download the code, you can use it, you can change it, you can do whatever you want. So to me, that's a very nice example of how university and the industry can shake hands for the sake of everyone. Just to give you an insight into why it is important to do experimental design, in medical physics, that can be detrimental, right? If you have the wrong diagnosis just because you didn't collect the data in the proper way, that's very, very sad. In the oil and gas industry, for instance, I mentioned that a single pixel can be millions. If you don't really understand what's going on in the subsurface, that can cost you even billions of dollars, right? Every well that they drill can cost $350 million. So, and 2 out of 3 are actually dry. So imagine how much money one can save an oil company just by being a little bit more thoughtful as for how you collect the data rather than just do the best with the data once it is already collected. So last topic is client interaction. So that's actually the most interesting aspect of working in the industry for me. You come from one perspective which is somewhat more academic compared to the clients. And they have their own world of idioms and world of understanding, and you would like to be able to draw some taxonomies from the two very different fields. It requires both sides to be open-minded. It requires you to generalize, abstract, reach out, not stay in your own comfort zone, as I mentioned. One of the more difficult things is actually to critically challenge convention, practices, prejudices in both sides. It's easy to just point a finger to the other side, but that's the most difficult thing. So whenever you work with the industries, you feel a lot of resistance. This is what they've done for the last 20 years. It works. Why should you touch it? You should ask yourself still that question. I know that when something works, it's great, but maybe you can do better, and that's a good takeaway for you guys. Often when we work with clients, they do ask questions that we completely didn't anticipate. And that brings into bear new interesting problems that otherwise we would never even dreamed of working on. So there are some accidental discoveries that happen through that process, and that's great. Here is an example of which. So when we look at medical physics versus geophysics, there's a lot of taxonomies. These two fields are very, very similar. Both problems have structure, uncertainty, non-trivial correlations. The acquisition techniques for the data are very similar. The mathematics, the physics is the same. The main difference is really the scale, right? But if you ever think that they are really too far apart, you can always see this Rushmore mountain where you can see that the head and the mountain can be one, right? So you can always bridge between the things. So here is a quick example as for taxonomy exploration. This one is again with it's work that we did with some oil company. They typically prescribe the control. So they inject water into the subsurface, and that water displaces the oil, hopefully, into the production wells, and then they pump it out. And typically they prescribe those controls to satisfy one important goal, money, right? It's all about the money. They would like to maximize production, and everything which is not directly related to that for them is a trouble. So when we came to them and we told them, look guys, if you would manipulate your controls a little bit, maybe you can get more information, right? This is not something that we invented. People have been doing that thing in medical physics for many, many years, right? When you would like to understand what's going on inside one's head or inside one's body, you would, if you're looking at CT, you would shine radiation from different projections, not from a single projection. And by manipulating those controls, you can actually characterize or identify better the system. It was very, very difficult to convince them to do that, right? As I mentioned, there is a lot of prejudices and a lot of fixation sometimes. But when you do that, you actually get far, far superior results. And this is just an example of how those taxonomies can come into reality. Another quick example of taxonomy. So I work closely with the speech recognition group, and apparently speech recognition you can form as an ill-posed problems, both for classification purposes and both for learning the predictive model, or which is what associates the input and the output. I just wanted to provide you this example to show you that, you know, taxonomies can be found everywhere, right? It's really about being open-minded. And the last thing, and this is really to me the most important advice and the real important take-home message, and it's not only for research. Actually, it's good for life, right? If you're married, you'll understand me. Two-way communication is really important. You need to bridge across jargon and cultures. You need to learn and try to understand the other side and understand it really deeply, not just observe, but try to do more than that. You need to be able to explain mathematical notions intuitively so that the other side will understand where you come from. It's not only about, you know, here are the results, good luck, right? You need to have a full handshake with the other side to make sure that things are completely appreciated in the other side. And the last thing, which is something that I learned from my own experience, often in a painful way, you need to conduct research that actually has true impact, not for you. You need to make sure that that impact is valued and appreciated in the other side. You need to make sure that you're capable of reflecting and make sure that the client's metric appreciate that research. So I'll give you one last example for that. We worked with the National Environment Association in Singapore. This one I can reveal. And we wanted to be able to predict severe weather conditions, severe rainfall, in very short amount of time. So this rainfall actually occurs over the course of minutes. So the conventional weather prediction models that run only for 6 hours cannot really handle that. We need a very different strategy, reduced physics, because again, we need to compute something very, very fast. We developed a beautiful, really beautiful mathematical formulation. We combined data-driven with physics-based formulation, state-of-the-art discretization methods. Everything was beautifully lined up, and eventually we failed. I don't know whether you can see that funny line. The blue line shows what we believe the mass flux, or the collective mass of water did, and the green one, unfortunately, tells what reality did, against all mathematical sense, right? So later on, I actually discovered that specific problem is still an open problem. It's been an open problem for many years in that community, but you know, I didn't learn much about the background, and I didn't appreciate that. And you know, sometimes you need to be able to also admit mistakes. So really, the last message is this one. At the end of the day, we do research, right? And if this guy said something which I think all of us can relate to, if we knew what we were doing, it wouldn't be called research, right? So thank you very much, guys.
Maybe we can take